Hello, guys. So I'm the last one before the cocktail, and I'm going to talk about energetics of quantum technologies. If you look at the existing digital technologies, you hear a lot about the blockchain, the Bitcoin consuming a lot of energy, and even more than we would have expected a while ago. You hear about ChatGPT and AI. We even hear about so-called frugal AI because we discovered that AI is consuming too much energy. And what happened in those two cases, and these are not the only ones in the digital scene, is that most of the thinking about optimizing the energetics of those new technologies came after it was developed, after it was commercialized, after it was deployed in a large scale. We have a chance with quantum computing, and Dave did show that it's not yet working well. We have a long time to go to create workable quantum computers and also other quantum technologies. So it's about time to think about it early on to avoid creating a nightmare scenario where we would have, let's say, a large-scale quantum computer who would consume maybe as much as a nuclear plant, power that can be generated there, or that even quantum communications deployed at a large scale would add a lot of energetic burden to telecom operations. So these are the kind of things that make sense to be thought out now. And this is what the Quantum Energy Initiative is all about. And I'm one of the co-founders of this initiative. It came from a statement from my friend Alexia Ofev, who's now leading the MaduLab International CNRS Lab in Singapore. So it's a French lab based in Singapore, but with a lot of international collaborations, mostly with Singapore, but with other places. And so she published back in June last year this paper, which explains why it makes sense to think about it now. And so we ended up with creating this initiative. But the initiative is not just a statement. It starts with a lot of questions and scientific questions. The key questions we ask are the following. One is, it's kind of twofold. Could we benefit at some point from a so-called quantum advantage that would be energetic in nature, not just in speed up or in quality of computing? Or could we end up being in a kind of dead-end situation where the energetics would be a showstopper to deploy at a large scale those fault-tolerant quantum computers? So it's the two sides of the same coin. So we have to be positive. So we have to think about the ways to make sure that we avoid being in the second situation, I mean, in a deadlock situation. And we have to make sure that people work together. There are some fundamental questions that are asked as part of this work. So are there fundamental limits at the qubit level, at the electronics level? For example, one of the questions I've been asking myself is, we know about the fundamental limits of what's happening at the qubit level, at the nanoscopic level. But for example, there's not much knowledge about the limits of control electronics, for example. What would be the minimum energy required to create a microwave that drives superconducting qubit, for example. And we have to know that, and we have to understand that to know where are the limits and what we can reach when we build those billions or millions of qubit systems that are fault tolerant. Other technologies beyond quantum computing are also important. We don't know yet what's going to be the scale of the market for quantum communication on one hand and on quantum sensing on the other hand. So today, these are narrow market. But who knows? I mean, if QKD and quantum communication and quantum internet become a broad, I would say a broad market involving all telecom operators worldwide with satellites, with a lot of repeaters, which are key components of those networks, then scale will make it important to look at the energetics of the system. And sensing is about the same. Today, quantum sensing is a very, I would say, selective market with a micro gravimeter used to detect what's underneath the ground or stuff like that. But there are also opportunities to create a very powerful detectors for autonomous cars, for example, where the market could be much larger. So again, if the market gets big, gets large, it makes sense to look at the energetics of those systems. So at this point in time, we are heavily focused on quantum computing, but other categories of quantum technologies are also a good target to think about those things. So what are the goals of this initiative? So far, it's just a community So we are building up a community of researchers and industry vendors that care about those issues I mentioned. The second is it's about improving, because we couldn't say it doesn't exist, but improving the collaboration between various stakeholders in the food chain. So making sure that we have more collaboration between all the parts of physics, all the parts of electronics design, cryogenics, algorithm design, compiler, transpiler design, all those people working together, sometimes in silos, should probably work better together. So it's about creating a kind of new line of research, making sure that people have a better understanding of how the stacks are connected to the other, like the big square stacks from Dave. So making sure that we have a better connection. And there's probably a lot of work to be done there, both at the fundamental research stage and connecting fundamental research and industry vendors. The third question is about how can we create a methodology to assess the efficiency, the energy efficiency of those systems? How could we measure it? How could we benchmark it? And this is a new discipline as well. So there's a lot of work going on at ISO, I3, and so on, where there are some contributions needed in that space. And the QEI will be one of the stakeholders proposing tools and methodologies and benchmarking approaches to look at the energetics of those systems. The last one is, if you just look at quantum computing, is look at all the categories of qubits. And for example, if you look at the photonic qubits and neutral atom qubits and superconducting qubits and photonic, all these are very different. I mean, if you look at the energetic spendings of those systems, it's positioned at very different levels. Usually people fear about the weight of the cryogenics in superconducting qubits. It happens that the biggest weight is with electronics when you scale. Control electronics consumes today more than 100 watt per qubit. So let's say you have 20 million qubits. If you multiply that, you end up with a lot of energy. It's besides the cooling and besides all the classical computing that controls surface code or various QEC systems. So we have to look in a very open way at all these technologies in a so-called holistic way. Today, we have a scientific board. So these are the names of the people. We are very glad to have representatives from various continents: North America, South America, Australia, Asia, even Middle East, with a researcher based in TII in Abu Dhabi. So we have a broad team, good diversity, and we will expand that team. It's just the beginning. So that's where we are today. Actually, I had a meeting with the board just before starting that event. We have the beginning of a community. So we first started to publish a manifesto. It was a similar story with the manifesto from the EU flagship. Some of you remember the manifesto from the flagship, which was launched, I don't know, 2016, Eleni, maybe 2016, something like this. And it landed, it became the EU flagship that was announced 2 years later in 2018. And today we have a community of about 300 people from more than 40 countries, representing both the industry and academic research. And it's growing every day, so I had to update the slide this morning for that reason. We also have an interesting involvement from industry vendors. So the vendors we have right now are those in the middle. So you see various companies, mostly from Europe, like IQM, Parity QC, iQuantum from Spain, Kipu from Germany, and of course, because we started in France, a couple of French companies. And we have some labs at this point. It's interesting because we found out it was easier to get the endorsement, formal endorsement from companies like Victor, Guillaume is over there, and Pascal, we have George over there as well. I want to avoid missing somebody. So it's the toughness of this. But we have some research labs, for example, or research organizations like PCQT. Eleni is representing this organization here in the room. Sorbonne Information Center, Majulab from NCQT from Singapore, WACT, which is the organization where Janine Spetsaucer, one of the co-founders of the QI, is working. And we also have two different kinds of stakeholders here. And the most interesting ones are OVH Cloud, HQI from France, and also CSC from Finland. These are the potential users of quantum computers, because those guys will deploy quantum computers. So we know, for example, that the Pascal quantum computer is going to be deployed at HQI in France. It's going to be deployed as well in Germany. And CSC is going to deploy probably some computer from IQM. So it's interesting to see the connection between the user, the organizations who will deploy those systems, and they will have their own production constraints and energetic consumption, or even water or whatever other thing. And it's interesting to connect the dots between all these players as part of this initiative. And then we have ecosystem organization, mostly from France right now. It's going to expand probably to others. That's just the beginning. So we have 29 partners as of May, and we started aligning partners back in September last year. We also are organizing, if you are interested, the first workshop for this initiative. It's going to be in November in Singapore. So if you like exotic places, it's in the equator. It's a nice place to go. And we already have a very good line of speakers announced, like Michel Devoret. Those who know superconducting qubits probably know Michel. So he's one of the key guys at Yale with Rob Shopkoff and Steve Gervin. We have Anne-Hee Paik, who spoke today, this morning in the Q2B. She's one of the leading researchers at IBM. We have Peter Zoller from Innsbruck. Miles Gu from Azure Lab is a very interesting guy in the, I would say, in the, with another guy. I'm missing one here. Sorry, forget. So there's a mix of people from the quantum physics side, quantum architecture side, and people who know also a lot about software side and algorithm side of quantum computing. So it's going to be a very interesting place. We will end the abstract submission by the end of this month. So we already have about 23 submissions. So it's good for a new topic that's emerging from the wild. And we expect to have very interesting proposals from various researchers. And interestingly, what we found out in both research, academic research on one end, and with industry vendors, is that topic is very attractive for young people and young researchers. They are really motivated to look at this. Probably they're more sensitive to older people, to the future of this planet. So that's why we have a lot of people like this. So the name I forgot, yes, is Kwek here. It's from CQT and Azure Lab in Singapore. He's one of the guys, leading guys with a good understanding of what we can do with Nisk algorithms. So it's interesting to look at the Nisk systems for this respect. Now, I will stop talking about the QAI as a kind of organization. I will try to showcase some of the thinkings that we have behind this and at the engineering challenges that are behind the initiative. If you look at like Dave, at the key challenges we have today, one of the key challenges we have with quantum computing is scaling. So we know that whatever the technology, even taking into account bosonic qubits like the ones from Norquantic or Alice and Bob, we will need zillions of qubits to do something usable. So we know that we'll need at least hundreds of thousands of qubits to make things workable. And this will create a lot of pressure for the energetics of the systems, because we will need as many control electronic systems. Well, it's even true for trapped ions, neutral atoms, and others, that even though it can depend on the type of qubit. So that's going to be a key challenge. That's what's on the bottom left, electronics, cabling, and cryogenics. Of course, we will need to improve the stability and the fidelities of those qubits. I would say, looking at all the challenges around, it's probably the biggest one. I mean, you can fix cryogenics, you can fix electronics, probably, because it's classical technology. But making sure that many systems get entangled at a very large scale is probably a very complicated thing. It involves some quantum thermodynamics at some point, but it's very quantum physics based. Then you have the scaling of QEC, quantum error mitigation for Nisk or quantum error correction for FTQC. And this shows the tough connection, the complex connection between the physics of the qubits, the connectivity between the qubits, the quality of the qubits, the algorithms, the kinds of error correction codes that you use. All this is connected. So hardware, software, architecture, there's going to be a lot of things to improve there. Of course, if you look at quantum interconnect and data loading and quantum memory, those are going to be huge issues to address to make sure that we have workable quantum systems. And probably this part of the quantum computing is underlooked. Some people knows that if you want to have an Oracle-based algorithm like Grover or whatever, you need to access some classical data at some point, and this has to be efficient. And right now, we don't have the technology. So we will have to develop those technologies, and we will have to look at the energetics of those technologies as well. Quantum interconnect is the same. If we want to interconnect many QPUs together, we will have to work this out as well. So these are the kinds of challenges that are connected to the energetics of the system, and we need to look at this from a holistic way. So this is a zoom for one of the slides. I can show you the complexity of what has to be addressed to scale just a superconducting qubit system, whatever the technology you use. So if you look at the drive, so the green is readout, the red is driving the qubits. So we have about, let's say, 12 problems to solve, just to scale. So one example is, how do you scale the circulators, or how do you scale the amplifiers? Those are here. So right now, due to the way we multiplex signals, we have to have about one amplifier for every 8 to 9 qubits. And it's heavy. I mean, it's 3 centimeters times 3 centimeters times about 1 centimeter. It's bulky. And let's say you have 1 million qubits. You count the number of all those 4 things you have here, divided by 10 for your number of qubits. It's heavy. And sometimes it's consuming some power. So you have to look at this. You have to look at the way you multiplex your cabling, because right now you have at least 5 cables for each and every qubit. And all these cables are dissipating energy at each of the stage of your cryostar. So you have to look at this. One way to look at this is to create a modeling, a kind of digital twin of your system. And that's why Alexia and her team, and Robert Whitney and Marco Felusasiani did last year. They published a very interesting paper, which is kind of both science fiction on one hand and a very good holistic approach with the way you optimize the system. They try to find a way to look at the interaction between all these figures of merit. So they looked at the interdependencies between the quality of the qubits, the surface code that you use, the even the characteristics of all the cables, the amplifiers, the multiplexing, and they saw those interactions. So for example, one interaction that is very interesting is if you improve by 1 order of magnitude the quality of your qubit, and we know it's a tough game, you improve by 1/100 the energetics of the system, the total system. The other outcome of this work was to find out that it's not necessarily good to put your control electronics at a low temperature. It's better to put it at room temperature if it's a CMOS technology. But on the other way around, if it's a superconducting electronic technology, like the one from SICK in the US, then it makes sense to put it in cryostar. So these are the kind of trade-offs that were found in that paper. And this paper is just the beginning of probably a new series of papers that look at the interconnection between all the technologies you have in a system. So it's going to be useful to do the same kind of study for any kind of qubit, and also in analog computing. One big question is, how about Nisk? By the way, there's an open position for studying this in Alexia's team in Majulab for a postdoc. Will we have some energetic advantage with Nisk? It's an open question. We don't have the answer. First is, how can we make Nisk usable? That's the first question. If we can make a Nisk usable, we will have a quantum advantage. It's probably easier to get an energetic advantage in that case than in the case of a large-scale fault-tolerant system. But we first need to have a workable system. So good quality enough qubits, like the 100 times 100 challenge from IBM, maybe even more. Workable algorithms. Algorithms typically like VQE that handle chemical simulation that run in a reasonable time also. The time constraint is important. And interestingly, there's always a trade-off between time and energy. If you want to execute such an algorithm in a reasonable time, and sometimes the current estimates for some algorithms is counted in hundreds of years. So if you want to be able to run this in your lifetime, you have to multiply the number of QPUs running the same shots, and so that we end up with having a bigger energy consumption, at least concentrated in less time. So it's going to be an issue to manage this trade-off. And when you look at the way a variational algorithm is run in Nisk architectures, like what you see here, is you have the multiplication of many time constraints. So you have to run more or less depth algorithm. Then you have a measurement based on different polystrings because you have different bases to measure your results. And then you compute those polystrings up to 1 million times. Then you have got the overhead of error mitigation, the cost of processing, the cost of ansatz preparation. All of that has to be done a couple times. And then in the end, you have a heavy burden on your computing. And this has to be taken into account. And when you look at the quality of existing qubits right now, well, nobody is in the usable zone. You don't have enough quality with an enough number of qubits. You should have at least 3 to 4 nines of quality. It doesn't exist yet, so that's one of the challenges for the vendors. Another question is, how about analog computing? Right now, if you look at analog computing, whether you take a D-Wave system or a system from Pascal or Q-era, these have some characteristics that are interesting. First is they are offering the best Q-score. Q-score is this benchmark from Atos that computes the largest size of max cut problem that you can solve. And currently, these are the best systems available. Currently, it will change probably over time. So the key question is, will it scale? To what extent will it scale? When will it be impossible to scale and they will have to go to gate-based models? And how about their own energetic footprints? And so, for example, if you look at the energetic footprints of the Pascal system or the Q-era system in the US, these are very advantageous right now. It's less than 20 kilowatt even taking into account the forthcoming generations. And they're able to simulate many-body systems, many-body quantum physics system. It's looking to be very interesting. So this is a good question to be asked there. Another question is quantum communication. I already mentioned it, but when you look at the size and scale of the quantum network that will show up in the future, this will have to be studied as well. So you see, the QEI is not about having answers right now. It's about having questions, and it's about having a lot of people working together. And that's the goal. And it's a very interesting journey to be engaged there. And I offer you to be part of that game. Thank you very much. And here are the contacts for the QEI. Thanks.